Welcome to the debate. Today, we're diving into a really fascinating and, let's be honest, often confused area. It sits right at the crossroads of cosmology, plasma physics, and, well, how we actually observe the universe with our instruments.
Mm-hmm.
We're talking about the critical conceptual and I think observational boundaries between what's called dark plasma and something else people sometimes call ordinary plasma in a low radiation or, a dark mode.
Yeah, that terminology gets tricky.
It does. And this isn't just about word choice, right? It's pretty fundamental to how we interpret the huge amounts of cosmological data we're collecting. And ultimately, it impacts how we understand the very nature of dark matter itself. Misconceptions here, they could really risk misinterpreting what we see out there.
Absolutely.
So, our central question for today's discussion is this. Is dark plasma a truly distinct, hypothetical form of matter, something composed of unique dark sector particles with their own interactions? Or is it actually just a state of, well, ordinary plasma that happens to be operating in a low radiative dark mode that makes it hard, maybe very hard for us to see?
Right. I'll be making the case that dark plasma is in fact a fundamentally distinct entity, a real component of the dark sector. Okay, and I'll be challenging that viewpoint by arguing that ordinary plasma, even when it's very dim, even in its most quiescent dark mode, it still remains firmly within the realm of electromagnetic phenomena. It's fundamentally different from the electromagnetically inert hypothetical dark plasma, which is, our current picture of dark matter. So my focus will really be on those crucial differences in observational signatures and fundamental interactions.
Okay, let's start then. Let me try and clearly define what I mean by dark plasma. Now, this is a concept that's been explored by quite a few prominent researchers. People like Jay Alfred, Sean Curl, and Lottie Ackerman back in '08, Kaplan, Krnjak, and Ray Harman in '09, Maddie Hakenhimo and Christian Spiethman, J.D. Clark, and Robert Foote, Nitin Shukla, quite a list. They describe a hypothetical state of matter, and the crucial part is this. It's composed entirely of dark sector particles. Now, the fundamental difference here is, well, it's profound. Dark plasma does not couple to the standard electromagnetic field, the one governing light and all the forces we see and feel. Instead, the idea is it might interact via a completely separate force, maybe a dark electromagnetism, a gauge interaction that's confined exclusively to the dark sector itself.
A separate interaction altogether?
Exactly. So what does this mean for actually seeing it? Well, it implies dark plasma is invisible across all electromagnetic wavelengths. It just doesn't emit, absorb, or scatter photons in any known bands we can measure, from radio waves all the way up to gamma rays. None. Therefore, its presence, it can only be inferred indirectly through its gravitational effects. Things like the bending of light around massive objects, gravitational lensing, or those strange rotation curves of galaxies that don't match the visible matter. And importantly, this complete electromagnetic non-interaction, it aligns perfectly with the observed cosmic microwave background data for dark matter. It leaves absolutely no electromagnetic trace, which is precisely what we'd expect from a truly dark component of the universe.
Okay, I appreciate you laying out that theoretical framework for dark plasma so clearly. It's certainly an elegant concept for a potential component of the dark sector. However, the widespread confusion, at least as I see it, often crops up when this idea gets mixed up with what people call ordinary plasma in dark mode. So, just to clarify my terms, ordinary plasma is made of standard model particles, the usual suspects, electrons, protons, ions, and critically, it interacts directly and quite robustly via the electromagnetic force. This kind of plasma is, well, it's everywhere in the observable universe. It makes up stars, nebulae, even parts of Earth's atmosphere.
Sure, standard stuff.
Right. Now, when we talk about a dark mode for this ordinary plasma, we're really talking about a regime where it has very low emissivity. It might emit little or no visible light. But here's the key distinction. Low emissivity does not mean invisible. This dark mode ordinary plasma is absolutely not truly invisible across the board. We have a whole suite of powerful, modern instruments capable of detecting it across the electromagnetic spectrum. For instance, infrared and ultraviolet spectroscopy. They can reveal subtle but definite signals, vibrational and rotational transitions of molecules, or they can detect metastable atomic states in elements like nitrogen, oxygen, argon even, when the plasma isn't brightly glowing in visible light. And furthermore, our X-ray and radio telescopes, they're very adept at detecting things like bremsstrahlung, that's the radiation you get when charged particles slow down, or synchrotron radiation, and various specific line emissions. These are all, dead giveaways of electromagnetically active plasma. Even very low temperature, weakly ionized plasmas, the kind you might think of as dark, they exhibit quite rich spectroscopic behavior. This happens through nonthermal excitation, or rotational vibrational transitions that emit in the infrared, and metastable decay, which produces UV photons. We see these signatures routinely in places like planetary atmospheres, vast nebulae, galactic halos. It's observable.
Okay.
And crucially, this brings us to the cosmological data. If significant large-scale structures were actually made of ordinary plasma in some kind of dark mode, their inherent electromagnetic coupling, their interaction with light, would have left unmistakable imprints in the CMB anisotropy spectrum. We'd see specific patterns like acoustic oscillations and damping signatures. But those signatures are simply not observed in the CMB data that we attribute to dark matter. So this whole idea of dark mode ordinary plasma being observationally silent, it's really a misnomer. It is unequivocally spectroscopically active, just maybe outside the visible range. And this persistent electromagnetic activity makes it fundamentally different from true dark matter.
I see why you're hitting that detectability point so hard. And yeah, it's a compelling case for ordinary plasma. But let me offer a perspective that maybe digs a bit deeper, down to the foundational difference. The core distinction, as I see it, between dark plasma and ordinary plasma, regardless of how bright it is or whether it's in a dark mode, it really starts at the most fundamental level. What is it actually made of, and how does it interact? Dark plasma, hypothetically, is composed of entirely new dark sector particles. And these particles, they interact via a proposed dark electromagnetism, a distinct gauge interaction. So think of it like this. You know how particles exert forces by exchanging other particles, like photons for electromagnetism? Well, this would be a force mediated by dark photons, maybe, completely decoupled from our standard electromagnetic force. It's like a whole separate set of rules, electromagnetically speaking.
A parallel system, yeah.
Exactly. Ordinary plasma, though, whether it's burning brightness star or just faintly radiating in some galactic halo, it's fundamentally made of standard model particles, electrons, protons, ions. And it interacts, by definition, through the standard electromagnetic force we know and love. This isn't just a quantitative difference like, how much light does it emit? It's a profound qualitative distinction. It's rooted in entirely separate fundamental forces and particle species. It basically means they belong to different sectors of reality, at least as far as our current physics understands it.
Okay, that's a critical distinction you're making regarding the theoretical particle makeup and the fundamental forces involved. And I agree entirely on let's say, the theoretical distinctness of dark sector particles and the concept of dark electromagnetism. That part's clear. However, the widespread confusion that we're, trying to unpack today, in my view, it stems precisely from the terminology, especially that phrase dark mode. Ordinary plasma in dark mode is without any question still an electromagnetic entity. Its very composition, standard model particles, and its interaction through the standard electromagnetic force confirms this. Its darkness just refers to reduced luminosity, usually in the visible range. It doesn't signal a complete absence of electromagnetic interaction or, crucially, a change in its fundamental nature.
But the implication people might draw.
Exactly. We have to be incredibly precise here. Allowing the term dark mode to even imply a relationship to dark matter is a huge conceptual leap, and it's one that just isn't supported by the physics. It's a description of an observational state for normal baryonic matter, right? It's not some ontological shift towards the dark sector. Misusing this term, I think, risks conflating two entirely different physical phenomena, and that has pretty significant implications for how we interpret what we see out there. And let's push a bit further on this observational detectability point. Because, this is where the rubber meets the road, observationally speaking. My point is that dark mode ordinary plasma is demonstrably empirically not invisible. We have incredibly robust observational tools. This isn't just theory that we use for its detection across the full electromagnetic spectrum. Infrared and ultraviolet spectroscopy, for instance, are amazingly sensitive.
And just to be clear, metastable states are where an atom or molecule hangs on to energy for a bit longer than usual before spitting out a photon, often in the UV or IR. These are like, chemical signatures of these plasmas.
Sure, specific transitions.
Right. And on top of that, X-ray and radio telescopes easily detect things like bremsstrahlung, the breaking radiation from decelerating charges, and synchrotron radiation from charged particles spiraling in magnetic fields. Both are absolutely fundamental signatures of electromagnetically active plasma. Even in extremely diffuse, really low-density environments, these emissions are still present. So this empirical detectability, the fact that we can see these signals, and we do see them, it directly contradicts the concept of true darkness as we understand it for dark matter. It's not just dim, it's still electromagnetically active and, crucially, observable if you have the right instruments. The challenge is detecting its faintness, perhaps, not its inherent invisibility.
Okay, but I'm not convinced that let's say, the subtlety of detection for dark mode ordinary plasma truly blurs the line. Actually, I think it does the opposite. It highlights it. The very fact that you can detect ordinary plasma in any electromagnetic band, no matter how faint or how far outside the visible spectrum, is precisely what fundamentally differentiates it from dark plasma. Dark plasma, by definition, by its very proposed nature, is invisible across all electromagnetic wavelengths. It fundamentally does not emit, absorb, or scatter any photons, period. Its detection relies solely and completely on gravitational effects. There's no infrared signal, no UV, no X-ray, no radio emission expected at all from dark plasma itself.
So the absence is key for you.
Continued electromagnetic activity of dark mode ordinary plasma, however subtle, however difficult it might be to pinpoint, firmly places it outside the realm of what dark plasma represents. It remains an active electromagnetic medium. It's just operating at wavelengths our eyes or maybe even our standard optical telescopes aren't sensitive enough to or aren't designed to perceive easily. Dark plasma, on the other hand, is completely decoupled from that entire spectrum. It's a truly silent component of the cosmos in every sense except for its gravitational pull. This feels like a fundamental qualitative difference to me, not just a matter of degree or, limitations in our current detection tech. And this, I think, brings us to what I consider one of the most decisive cosmic constraints we have, the cosmic microwave background. Honestly, I'm not convinced by any line of reasoning that tries to allow ordinary plasma to somehow mimic dark matter, because the CMB provides just unequivocal, really robust evidence against it. Think about it. If those huge, large-scale structures that we infer exist because of gravitational lensing, the cosmic web, galaxy clusters, if they were actually composed of ordinary plasma, even in some super dark mode, its electromagnetic coupling, its interaction with light, would have left incredibly specific, detectable imprints in the CMB and isotropy spectrum.
The baryonic acoustic oscillations.
Exactly. We would see distinct patterns of those acoustic oscillations, those ripples in the early universe caused by sound waves sloshing through the coupled plasma-photon fluid. And we'd see specific damping signatures where these oscillations fade out because photons can diffuse out. These are the clear fingerprints of ordinary baryonic matter interacting with lights back in the early universe. And the crucial point is, such imprints were not observed in the parts of the CMB anisotropy that correspond to dark matter's gravitational influence. That absence strongly supports the non-interacting nature of dark matter, including any potential dark plasma component with photons. It unequivocally confirms its distinctness from any form of ordinary plasma. The CMB acts like this incredible cosmic probe, maybe an acid test, that separates the stuff that talks to light from the stuff that doesn't.
Okay, I'm sorry, but I just don't buy that the CMB data somehow supports a blurring of these lines. Actually, I think it underscores the very distinction that I'm making. Let me tell you why. I fully agree on the critical role, the unparalleled power of CMB data. It's phenomenal evidence. But this evidence supports my argument for a clear distinction. It doesn't challenge it. The fact that ordinary plasma, even in a hypothetical dark mode, would indeed leave a detectable electromagnetic signature on the CMB, just as you've described, with the acoustic oscillations and the damping, and the crucial fact that such a signature is absent for the structures we attribute to dark matter, well, that's precisely why ordinary plasma is definitively ruled out as being dark matter.
But that absence points to something fundamentally non-electromagnetic.
Exactly. This evidence, essentially, it puts up an insurmountable barrier between the two. It reinforces that ordinary plasma, because of its inherent electromagnetic nature, simply cannot constitute the universe's dark matter. The CNB tells us very clearly what dark matter is not, precisely because of its lack of electromagnetic interaction in the early universe. So conflating dark mode ordinary plasma with hypothetical dark plasma, that risks misinterpreting this really crucial cosmological data and potentially leads us down completely the wrong path in trying to understand the universe's makeup. It's a powerful, unambiguous discriminator, and I think it strengthens the case for two fundamentally distinct phenomena.
I see why you frame it as reinforcing your distinction, using the CMB as the divider. And I agree, the CMB data is absolutely critical here. But let me just offer a final perspective, maybe, on the conceptual clarity we really need in this field. My core argument, it still remains this. Dark plasma represents a fundamentally new conceptual construct. It involves hypothetical dark sector particles, maybe a completely separate dark electromagnetism. This isn't just a subtle variation on plasma we know. It's a profound departure from ordinary plasma, even when that ordinary plasma is in its most quiescent, its faintest dark mode. Ordinary plasma, no matter how dim it gets, remains at its very core an electromagnetic entity. It's tethered to the familiar forces of our visible universe. So, precision in our language and a deep, nuanced understanding of these distinct physics, I think that's paramount. Without it, we really do risk misinterpreting crucial cosmological observations about the true nature of dark matter. We might mistake an incredibly subtle form of ordinary matter for something truly, truly exotic.
That's a compelling summary of the theoretical landscape, and I absolutely agree that conceptual precision is vital. My concluding point really just reemphasizes that the persistent detectability, however difficult, and the inherent electromagnetic nature of dark mode ordinary plasma are precisely what carve out its difference from the truly electromagnetically invisible, gravitationally inferred dark plasma. The confusion, I think we both agree, often stems from that potentially misleading term dark mode, which simply needs very careful conceptualization. We have to avoid letting it conflate ordinary baryonic matter with the truly hypothetical, non-baryonic dark matter. Understanding these conceptual and these observational distinctions, well, it isn't just some academic exercise, right? It's absolutely vital for scientific clarity as we keep probing the universe's most profound mysteries.
Yeah, I think this discussion really does illuminate the subtleties and the complexities involved in trying to understand what the universe is actually made of. It definitely underscores the absolute necessity of using precise scientific language and making rigorous distinctions between phenomena.
Indeed. It really highlights the demanding intellectual work that's required to differentiate between things that might seem superficially similar maybe, but are actually, at their heart, governed by entirely different physics. And there's certainly, I think we'd agree, more to explore in the material regarding these fundamental concepts and their really profound implications for potentially new physics down the road.